Okay, we're recording. So, here's where we left. Oh, I forgot to pull the thing down here. This is where we left off. We were talking about what I'm going to call the calculus of level sets. Right? So the big idea, again, is that if you're on a level set, then the function's not changing as you move along that surface. If the function's not changing, that means that all your directional derivatives tangent to the surface are all zero. Directional derivatives, of course, are computed with dot products with the gradient. And so if the directional derivatives are zero, the dot products are zero, that means we have a perpendicularity. In particular, the gradient is perpendicular to all of the tangent vectors. Right? And if the gradient's perpendicular to the tangent vectors, then that means that the gradient itself has to be perpendicular to the surface. And so we get this result here. This is one of the big results of what I like to call the calculus of level sets. Notice it's just very different from the calculus of graphs, right? So, this is just a quick callback. I made a big deal a long time ago about we've got to really pay careful attention as to whether the picture we're looking at, is this a graph of a function I'm dealing with, or is this a level set? You really got to know which one. It really matters because the calculus looks so different, right? This business about this sort of derivative object being perpendicular to a surface, there isn't anything like that in the calculus of graphs. So, anyway, really big deal. Always make sure to pay attention to what's the nature of the picture you're looking at. So we're going to do something with that now. We're going to revisit an old question that we already know the answer to see kind of another way of deriving that result, namely how do you find the equation of a tangent plane? And previously we used what I'm going to call the calculus of graphs. We viewed the tangent plane as being the graph of the linear approximation, and in the linear approximation we did calculus. Okay. All right. Let's take a different point of view, though. Now, same circumstance. We've got a surface that's a graph of a particular function. Being as it is a graph of a function of two input variables, it's a surface like this. And there's a tangent plane here that we want to find the equation of. Tangent, in particular, at this point. And now, again, there's a couple of weird things to say about that point there, where we want to talk about the tangency. Because we're in this weird world, we're in the graph. We're looking at the graph picture, which means that on the one hand, the point on the graph has 3 coordinates, because it's clearly a point in space. But as far as the function is concerned, I mean, what are the inputs to the function that define that point on the graph? Well, it's just the first 2 coordinates, because after all, only the first 2 coordinates are input coordinates, and then the third coordinate is the output value. F. Okay, so again, that weird little story, and we talk about how very often we'll conflate these 2 points for just ease of language. But when you're doing the algebra, when you're doing math, you do have to keep in mind which one do you actually need, depending on the circumstance. Okay. All right. So that being the case, this being our setup, how are we going to use the calculus of level sets? This isn't a level set as written. Okay. Well, yeah. So write it differently. Right? Now, I've done this move before. Here, we have an algebraic expression representing this being the graph of the function f. Graph, because I'm setting the values of the function equal to a variable. And so we're looking at the graph of this function f, whatever its formula is. There. On the other hand, same exact surface. Morally identical equation here. All you gotta do is just kind of take the one term and move it over to the other side. It doesn't even matter which way you go, particularly. Right? Having done basically no algebra, notice that it's now written as a level set, because we've got something set equal to a constant. It's a level set of this entirely different function called g. the thing that's being set equal to a constant, right? The thing whose level set we're looking at. Not the same as f. It's this other function. Function of three variables, mind you, right? X and y, so that you can evaluate this term, and z, because that's another term right there, right? So function of three variables. All right, so now that we have it written as a level set, we can kind of abandon all this talk about graph. I am now interested in finding an equation for the tangent plane to a level set. How are we going to find the equation of a tangent plane to a level set? Okay, well, no problem. This is this surface here is let's see here. I'm color coding. This is the surface G equals 0, and I know that the gradient of G is always perpendicular to the level set of G, this being, as it is, the level set of G. So the gradient of G being perpendicular to the level set, it's also perpendicular to the tangent plane, which means I can use this as my normal vector. And that's exactly what we're going to do here. We're going to compute that normal vector as just being the gradient of G. Okay, this gradient of this function right here. And it's kind of all over, but the shouting at this point, there's a little bit of algebra left to be done, right? We just have to take that gradient. Once you know the normal vector for a plane, I suppose we also need to know the what is this point that the plane passes through. We've already talked about that. A, comma, B, comma, f of AB, and with the normal vector and the point on the plane, we are all set. Let's see here. Here's the normal vector. The point on the plane is that, which again you can see there, and dot it up, multiply it out, shuffle terms around, and sure enough, you recover exactly what we should, namely this is the familiar equation of the tangent plane, right? We better get the same result, right? Two different approaches to answering a question, you better get the same answer. So good news that we do. And this is kind of a different approach to getting there. How are we feeling about this? Do y'all feel okay about this? Everybody see the strategy? How again, you can view a surface as a graph. Well, you can also view it as a level set, and you have different tools with the different calculus knowledge that we have for those different contexts. Yeah.
Can you explain what G is and why is the gradient vector of G equal to the normal?
So G is just another function, right? But it's a function that relates to the original function, like as I have described here. Let's see, let me zoom back in here. G relates to f in that I want the graph of f that I'm actually given and that I'm actually interested in, right? I want that to be a level set of something. And so what do you got to do to this equation to turn it into a level set of something? Well, you have to move terms around appropriately. And then in particular, you get that it is a level set because I've got equals constant. It is a level set of that expression right there. And that's what I'm calling the function G. So it's a function whose level sets, one of whose level sets is the graph of this other function. Yeah, it's a trick, in other words, to allow me, I was in a situation where I had a graph, I wanted to use the calculus of level sets, and this is the little zigzag you have to do to get from there to here. Right. Okay. All right. So I encourage you to check through the details that I've skipped over here and confirm that you can produce that this is the equation. As of course it should be. Here's an example. So we got a function given, and I want to find the tangent plane to the graph, just like in the previous setup. And so notice I'm going to do the same move that I did in the previous analysis. We are given initially that we're looking at the graph. Right? That's what a graph is. The graph of that function is what we're given. Here's my little zigzag where I just kind of shuffled things around a little, but I didn't really do anything particularly there. But now I can realize this as being a level set. See, something equals constant. Level set of now this other function. This then is the function whose level set is the surface that I'm actually interested in. So I've rewritten the question from a question about graphs to a question about level sets, and in particular level set of that function. So great, there's the function whose level set I'm interested in. That then is the function whose gradient is going to be my normal vector. Let's see here. Gradient is the normal vector. Of course, don't forget you do have to plug in the appropriate point, right? We're interested in what's happening. I'm going to, again, watch the language, but notice I'm about to conflate two things. I want the tangent plane at that point. Of course, I mean at the point above that point. Again, that's that whole graph awkwardness. So, appropriately, 2, 1 then are the x and y coordinates. And then I got to plug that in to the function to see what the z coordinate is. So when I say, at 2, 1, I mean, well, of course, at the point on the graph above 2, 1. And you plug that in, you get your normal vector, and it's all over. Everybody happy? A real quick observation I'll make. In fact, notice this trick doesn't even require that the original question be about a graph. I mean, it happened to be here that I happened to, I'd like to find the tangent plane to a graph. But all I really needed was to be able to rewrite whatever I'm given as a level set. Now, what is it about this equation that allows me to rewrite it as a level set? What is it about this equation that allows me to put all the terms on the left and have 0 on the right? The answer is that you can always do that with any equation. If you, however many terms you have on one side, however many terms you have on the other side, you can just move them all over to the other side and have stuff equal 0. So it doesn't even have to be a graph for this trick to work. Okay. All right. So last topic for this section, and in fact, last topic for this chapter. We're going to be into chapter 3 in just a little while here. Hopefully today. Fingers crossed. Knock on plastic. It's called Implicit Differentiation. You may have seen this in a single variable calculus class. I'm going to take a deeper cut into it than almost any single variable calculus, high school single variable calculus class does, because we really need to. In this context, again, single variable calculus has various luxuries. It's very low dimensional. It's a luxury, right? You can do everything with graphs, practically everything with graphs. That's really nice. And another luxury is it's dimensionally. It's always the same. You always have one input and you always have one output. And so you can get away with noticing, well, here's just kind of how it works, as opposed to understanding certain concepts. So there is a key concept that I want to talk about here that gets, again, very often blown off in single variable calculus classes. Here it is. Suppose I have some equation, and again, remember, any equation could be written with all the terms on the left. Again, interesting note, any equation can be written as a level set, right? And that's going to represent some curve. And suppose I want to look at a certain point on the curve. And suppose I'm interested in what I'm going to call locally, what is the curve doing around that point. And by locally, I mean, I want to restrict my attention to some myopic, narrow, highly restricted little piece of the plane here. And I don't really care about what's going on over here. I just nearby that point. I want to understand the nature of the curve there. So we call locally. So locally, can I view this equation, even though I have not solved for y? Does it Yeah, but in effect, unstated but unavoidably a consequence of what's written, can I view y as being a function of x? And we say, question then, can we implicitly, again, not having actually solved explicitly for y, but implicitly can I view y as being a function of x? Again, locally, just within the yellow here, near that point. And of course, yeah, absolutely in this case, looking at this particular point, because we look at the vertical line test, and the vertical line test passes just fine, right? Every vertical line hits that curve locally. Again, just that part of that curve, we ignore the rest. Exactly once, and so, yeah, no problem. Y is a function of x locally near that point. Okay. All right, what about this point? Now, a lot of people will mistakenly say no here because they think, okay, well, look at vertical lines, and vertical lines, we've got a problem, and no matter how small we restrict our attention, don't we have multiple hits from these vertical lines? Right? So it's tempting to say y is not a function of x. But the thing is, you got to keep in mind, we're talking about locally, right? And locally, again, means that we're only looking nearby that point. Not just nearby these values of x, but nearby that point. Right? Excuse me. And nearby that point, and therefore ignoring everything else, let's see here. Then vertical line test, fine and dandy, no problem. And yes, locally, y is a function of x. There. Okay. You are going to have problems sometimes, though. The problem in particular, for example, would arise there, where again, no matter how much you restrict your attention, if you look at this piece of curve, however little it might be, locally, I cannot view y as a function of x because, again, no matter how much I restrict it, I'm going to have multiple intersections there. So here we have an actual problem. Everybody with me? Okay. So what we're going to be interested in is figuring out how to distinguish cases like this, where no problem, yeah, sure, you can view y locally as a function of x, from cases like this, where, you just, it's not going to work. You cannot, in any sense, locally view y as a function of x. How do we tell the difference? So, does everybody see the question? Now let me try to explain to you why we would care about such things. A lot of people would say, who cares? Just a weird sort of arbitrary abstract math problem. So there's a really good reason why we would care about this, and that is that at a point like this red one, you not only cannot compute dy dx, but you can't even ask the question. It's not that, good faith, we want to compute the derivative of this thing called y. There is no y. Y is not a function. We take derivatives of functions. Functions very specifically. We do not take derivatives of curves. Right? This is one of the big reasons why we have to distinguish between graphs of functions versus functions. This is just not, in any sense, y is not a function locally there. So you can't take its derivative any more than you can take the derivative of a bicycle. It's just not. It doesn't make any sense. It's a disk. It doesn't. Nonsense. Right? So, we would like, right, if we're studying this curve, to be able to talk about dy dx with the understanding that by dy dx what I mean is, I want to, at, for example, a point like this, I want to be able to talk about with the slope of the tangent line. In other words, I want to locally view it as a graph so that I can establish that there's a tangent line. I want to talk about its slope. I want to be able to do basic calculus. And at points like this, where y can be viewed locally as a function, you're in business. It's fine. It's no problem. At points like this, you can't even write down dy dx. You're making up nonsense. And that's a problem. right? That's for mathematicians. That's a big worry. Okay, so it turns out there's a really good answer to this question. It goes like this. Suppose you are at a point where there is a problem. By the way, I'm going to be extremely not rigorous about this. I want y'all to have good intuition for where the answer comes from. I want it to make geometric sense, but I'm going to commit some little math crimes here. And don't worry, you're not going to probably notice, but I'm leaving a lot of the rigor out on purpose. So, so this, you can see here's a problem point, right? We have a problem there. And the problem is that we are at that point, locally near that point, we are going to fail the vertical line test. And we're going to fail the vertical line test like so, because at that point, the curve is in the process of wrapping under itself. It's the fact that the curve, was here and then wrapped under itself and got to there that causes the failure of the vertical line test. Yeah? Okay. All right, so the curve is wrapping under itself. Why is it wrapping under itself? Or let's say this, what else can I say as a result of it wrapping under itself? Well, it has a vertical tangent line. Right? If you're at a point where it is at the instant that it is wrapping under itself, then at that point it must have a vertical tangent. If it wasn't a vertical tangent line, then it wouldn't be quite ready to wrap under itself just yet. If it has a vertical tangent line, I'll note that, that means, now keep in mind, we're looking at a level set here after all. Right? Then the gradient of the function whose level set we're looking at, of course, right? Calculus level sets. The gradient would be horizontal, right? Because the gradient's perpendicular to the tangent line, and so if we have a vertical tangent line, then we have a horizontal gradient. And now, if you think about it for a second, and keep in mind that the gradient, I can write down the equation. The coordinates of the gradient are partial of f with respect to x, partial of f with respect to y. That being horizontal means that it doesn't have any upward or downward component. Horizontal means, in other words, that is 0. Everybody with me? Yes.
What if it had the vertical tangent line, but if it's this way?
Oh, yeah. No, I'm assuming here that we have an actual problem. Yeah. No, what you described, not a problem. And just I'm considering specifically if we have a problem. Does that make sense? No, and you're right that if I tried to turn these arrows around the other way, then it doesn't work. Absolutely right. Yeah. Okay, if you have a problem, argument, this partial derivative has to be 0. Now I'm going to remind y'all, we talked about this thing called the contrapositive. The contrapositive of a statement is kind of turning it around backwards and upside down in some sense, right? And if you think about it, the contrapositive of this statement that we just demonstrated, that if you have a problem, that partial derivative has to be 0. The contrapositive is this statement. If that partial is not 0, no problem. This is what we're actually going to be, in practice, day in and day out, this is what we're going to be using. There's a certain partial derivative that you can take. And if it's not 0, then nothing like this is happening. You do not have a problem. And yes, locally you can view y as being a function of x. All right. So anyway, ideally this would have been treated in a single variable calculus course, but I understand that it's not kind of how it works. Yeah, all right, now here's the thing. Now we're in a multivariable calculus course. Now we're going to consider when we have more than just the two variables. What if we have three? And again, what if we have, some equation involving three variables like this? That's going to describe a surface. The surface, let's see, I guess I could do this in purple. The surface might look something kind of like that. Analogous question. Can I locally view one of the variables, let's say z, as being a function of the other two? And again, it's going to depend on where you're looking. If you're looking at this point right here, can I view locally? Again, I emphasize locally, so we're only going to look nearby. Locally, can I view y as being a function of, can I view z as being a function of x and y? In other words, do my vertical tangent lines in the direction of the variable that I want to view as being a function. Do I have any multiple intersection problems? Nope, not a problem at all. Right here, it's fine and dandy. Yes, locally you can view z as a function of x and y. No issue. But at a point like this one, let me do that in a different color. At a point like this one, we've got a problem. Right? At that point, the surface, not a curve, but this surface is in the process of wrapping under itself. You're gonna have multiple intersection points. You cannot, at this point, locally, in any sense, view z as being a function of x and y. It's not. It just isn't. There is no function. And so you certainly can't talk about its derivatives because it's not even a function. So this is what we need to understand again, that we need to kind of, reason through, how do we identify this bad news? And again, it's pretty straightforward reasoning. If you have a problem, the curve is wrapping under itself. If it's wrapping under itself, then it has a vertical tangent plane. If it has a vertical tangent plane, then it has a, hit the colors. Okay, there we go. It has a horizontal gradient. Right now, notice this is kind of just a rip-off of the ideas that we saw for single variable. Same thing. It's just three-dimensional instead of two-dimensional. It's a tangent plane instead of a tangent line. But same moral ideas here. Horizontal gradient. Again, the gradient being made up of a bunch of partials. And horizontal means that the component in that direction, in the direction of the variable that I want to view as a function, has to be 0. Everybody good? Okay. All right. So this generalizes, by the way, and this is the deal. If whichever variable you want to view as being a function of the others, that is the variable whose partial needs to not be 0. Again, we're going to take the contrapositive, and it's when this is not 0 that I know that I don't have this scenario, and therefore no problem. Okay. All right. So the big thing to remember: whichever variable you want to view as being a function, that's the one you take the partial with respect to. And so I've got that written here in the statement of the theorem here, and again, here's the easy to recall takeaway. Take the partial with respect to the variable that you want to view as being a function. The one that wants to be a function. Okay. All right. So in particular, wanting to view xi as a function, I take the partial with respect to xi. All right. Let's see an example. So here's a big nasty equation. Representing a surface, of course, because this is an equation in 3 space, right? There's 3 variables, x, y, and z. So it's some sort of a wacky surface. I have no idea what this looks like. The question asks if I can locally view x as being a function. Well, I can't solve for x either, because it's the equation is cubic in x. We don't know how to solve cubics. So we have a nasty algebra problem. We have basically an intractable algebra problem. Not quite, but pretty close. But nevertheless, I'd like to know, look, I don't need to actually solve for x. I just want to know, hypothetically, is there a function kind of that I can view x as being a function of y and z, even if I don't actually solve for it. So, the solution, again, the variable that you want to be a function is the variable that you take the partial with respect to. Right? Is everybody clear on that? Always take the partial with respect to the variable that you want to view as being a function of the others. And very importantly also, always take to use the implicit function theorem, the thing you're taking the partial of is the thing whose level set you're looking at. And that's, again, very important. This needs to be a level set. That was intrinsic to the argument that we made, right? So make sure you rewrite things such that you're looking at, you got stuff equals constant. Might be zero, but it doesn't matter. Stuff equals constant. That stuff, take the derivative with respect to whichever variable you want to be a function. And it's just a matter of kind of cranking it out at this point. We take this partial derivative. Boom. Right, nothing to it. We're interested in what's happening near this point here, so I need to evaluate that expression, that partial derivative, at the point x equals 1, y equals 2, z equals 3. And we get not 0. And not 0 means yes, you can view x locally as a function of y and z. I can't solve for it, but I know it is a function, and therefore I can actually talk about the partial derivatives of x with respect to y and z, because it's in fact a function. And if I were to say partial of x with respect to y, I know for sure that that's not garbage. That's not a nonsensical question. Everybody with me? All right. Okay. Next thing we need to talk about. So we've established that x is locally a function of y and z. Now, how would I tell? Oh, yeah, question.
If we do get 0, could we say anything then?
Now, if you get 0, then you just don't know, because it could be a couple of different scenarios, and the question from the back points to this. It could be, if you get 0, that you've got a situation like this, where it's momentarily a vertical tangent line, but does it pass the vertical line test? Yeah, no problem. Passes the vertical line test effortlessly. Yeah. As opposed to the actual problem would be like this, and again, it also has a vertical tangent line, but in a way that still fails the vertical line test. So, yeah, how to distinguish these two is a more complicated story, and that's not what we're going to get into. Yeah. Anybody? Great question. Anybody else? Okay, so how do we take the derivatives? There's a hard version of that question, and then there's the easy version. I'm going to show you all the easy version. If you want to see the hard version, come to office hours. I'll be happy to show you. It's honestly the same exact argument. It's just a little bit more appropriate, a little bit more thorough and complete, and most of which goes to things that don't matter. So I'm going to give you the quick version, and here it is. So we've got this function f. Let's see here, highlighter. We've got this function f. It's a function of various input variables, x1 through xn. And suppose that I have established that I can view xi as being a function of the other variables, let's just say. So I've established that can be viewed as a function. Side note, in other words, what I've done is I've computed this partial and I've determined that it's not 0. So let's just suppose. All right, so this is a function. that's the function that I now want to take a partial derivative of. And let's suppose that I want to take its partial derivative with respect to, let's say, x sub j. Here it is. Now keep in mind, xi is a function of, let's see how okay, xi is a function of all of the other variables. I'm taking the partial with respect to xj, viewing xi again as being a function of these other variables. When I say partial with respect to xj, what I mean is all of the other variables are to be held constant. So all of these variables constant, if there's any variables in that little gap, the constant, and then whatever might be down here, all to be held constant. So looking at this picture then, I actually have a pretty simple story. Most of the variables in this picture are constant by assumption of the fact that we are taking a partial derivative. The only two variables in this picture that are not constant are the blue and the green here. And, there's another thing that's constant. Don't forget, f is a constant, right? The whole point of this discussion is that f, we're looking at a level set of it. So f is a constant. Right? So there's our picture. Practically everything is constant. Right? So we argue as follows. We say, all right, well, look, if f is constant, then altogether the how this f here changes is a real simple story. It doesn't change. It's a constant. So if I were, as is described here, if I were to take x sub j and start wiggling it, right? If I start changing x sub j, I kind of erased the j there, didn't I? If I start changing x sub j, altogether, the amount that this f changes had better add up to 0. Because it's a constant, right? And, well, okay, how might that f change? Well, there's two different paths along which changes can propagate. On the one hand, if you change xj, well, look, f is a function of xj directly, right? And so, yeah, you're going to just directly, partial of f with respect to xj tells you something about how, one contribution to how f is changing. The other contribution is that as xj changes, xi changes, because xi is a function. And then as xi changes, then that causes a contribution to the change in f. So that's that term. So these two paths is really all we've got. And the beautiful thing about this is it doesn't matter how many other variables you have. It goes all the way down to x sub n. Right? Doesn't matter. They're all constants. Right? So no matter how many variables you have, there's just the two terms. And keep in mind what we were interested in now. We wanted to solve for this factor there, partial of xi with respect to xj. And, well, you can just go ahead and solve for it with some simple algebra. And here's your answer. It's that expression right there. Everybody see how that works? And here's the really good news. You can, and I think should, just memorize this formula. I do think the argument is also really important. I hope you'll understand the argument as well. But certainly make sure to memorize that formula. Okay, several things that I need to say about this now, though. It is very tempting. This is another situation where you've got to be careful not to step on notational landmines. And you'll recall that when we were talking about the chain rule, I pointed out you cannot view partial derivatives as fractions. They're not fractions. It just doesn't work. It doesn't work. And likewise here, because if you were to view these as fractions, then it's tempting to say, these cancel. And then my xi, that's the denominator of my denominator is part of my numerator. And it would seem that you would get this and not have any minus sign there at all. Wouldn't that seem tempting? You can see the temptation, right? So, why doesn't this work? Well, because these are not fractions. These are part of different stories, different scenarios, and you just can't write them as fractions. So, as a result, this minus sign, in effect, is very important. This minus sign is that which distinguishes the truth from a bunch of nonsense that is suggested by a complete misunderstanding of the notation, right? And that one minus sign is the only difference between valid formula and garbage that again suggests dramatic misunderstanding. So important with that minus sign. That's golly, one of the most important minus signs in the course. Be really, really sure not to forget that minus sign on the exam. It's well, anyway. Does that make sense to everybody? Okay. Alrighty. Now that said, I just got through trashing this argument about, canceling these and moving this up to there. That said, it is a nice little memory tool. I'll give it that. Right? So, the argument that I made here assumed that you were going to have various input variables that were all named x1 through xn, right? And this tells you how to take a certain partial, implicit partial in that context. Well, what if they were named a different name? Do I need to have new versions of this formula for every possible collection of variables? That's silly, right? So what is nice about this argument is that you can use the garbage argument as kind of a convenience. So this is whatever variable you're taking the partial of. This is whatever variable you're taking its partial with respect to, exactly as if there was a cancellation, which of course there absolutely is not, right? And then just don't forget your minus sign. So whether they're called x1 through xn, or whether they're x, y, z, w, or maybe they're pqrs, whatever, right? Whichever partial you want, write down what would seem reasonable, add a minus sign. All right. So let's see an example. Suppose we've got this same surface that we saw before, by the way, and let the record show that surface near this point, we have already established that x is locally a function of y and z. I'll remind you, back up to here, we have established, is it locally a function of y and z? Yes, it is. So that's been done. So I should call this the second part of that same example. Having established that it is locally a function, and therefore, because x is a function, I can talk about its partial derivatives. Next part of the question, how would I compute this partial of x with respect to z? So the first thing that I do is I write down the formula. Now this is just a rip-off of the formula from the previous page. Notice that the thing that I want to take the partial of goes where, again, the fractional interpretation, math crime, right, would suggest it would be. And then the thing that I want to take the partial with respect to, we put it where, again, it would seem like it should go. We absolutely triple check, make sure not to forget that minus sign, because that's the minus sign that turns it from garbage into a valid statement. And there you go. There's your formula as pertains to this setup. Does everybody see how I translated the formula in this context? And now it's just you got to punch things up here. There's a little bit of algebra. The partial of f with respect to z, right? So take this function f, take its partial with respect to z. You get that. You take that same expression, take its partial now with respect to x, and that gives you this. And plug in the point in question, and boom. Okay. Everybody with me? Now, last comment on this, and then we're going to go on to chapter 3 for a few minutes. How do these questions in practice show up? And there's a certain sneakiness. There's a danger kind of in how these questions tend to come up. Now, I've carefully phrased this one where first I directly address immediately the question, wait, is this thing even a function? And then having established that yes, it is indeed a function, I then go on to ask the reasonable next question. Oh, okay, well, what are its partial derivatives? Okay, in practice, that's not how questions come to you. In practice, it's going to be something like this. Hey, here's a surface. Compute partial of x with respect to z. And the way that question is phrased, you'll notice it's kind of subtext assuming that x is a function. There is nothing about how this is written here that establishes that x is in fact locally a function of y and z. So the question is arguably presumptuous, assuming that the thing that it's asked you to compute isn't garbage. Right? But this is how the questions tend to come in the real world. In the real world, you're looking at something, and the reason you want to compute the partial of x with respect to z is because x, y, and z are variables that are involved in things that you're doing things with, and you need to know that partial for a reason that's related to what you're doing. Right? So you have to be consciously heads up of, they asked me to compute a partial of a thing that has yet to be established to be a function. We better apply the implicit function theorem first. Right? So again, that's part of your job. That's part of the student's responsibility to look at a question like this, just looking only at what I have highlighted in green, and realize that step 1 is to establish whether x is a function. Step 1 is to do all of this. Right? This is step 1 of such a function. You have to, indicate, hey, I need to establish that this is a function, do the appropriate algebra, draw the appropriate conclusion. Step 2, having established that it's a function, step 2 is to do all this down here. Everybody see what I mean? Yeah.
So if you didn't check to see if it was locally a function and just tried anyway and it wasn't, would you just get a divide by 0 situation?
You probably would. There are some situations where there would be an algebraic cancellation that would make the denominator 0 kind of go away. But that's not really the worst part of it. The worst part of it is if you start writing down derivatives of things that you don't even know if they're functions, then it's kind of like if you were trying to reason through some non-mathematical thing, and you're like, okay, so let's first assume that Snuffleupagus is in the next room and wants to come say hi, and then you reason from there. And the point is, your reasoning is all based on stuff you haven't established, and it's just not valid mathematical reasoning. It's importantly that's not math. Does that make sense? Yeah. So it's not because you want to protect yourself against possibly dividing by 0. That's not really the problem. The problem is you want to protect yourself from writing down garbage. Yeah. Does that make sense? I hope that's satisfying.
Yeah.
Okay. Yeah. Cool. All right. Yes.
So if the partial of the function with respect to the variable we want to establish is a function of the other variables is 0?
Yeah. Then you say, I can't even establish the thing's a function. What do you mean? What do you mean compute the partial? It's not even. I have no way of knowing it's a function. Yeah. Or you could try to establish it's a function in some other way, right? Like you could literally try to solve for x. Now here you can't. But if it were algebraically simpler, then maybe you could actually literally solve for x. In which case, then that establishes that it's a function, and then proceed. Okay. All right. So so we've got a few minutes left. We have 1 minute left here. Let me just lay a little groundwork. This will just take a second. Into section 3.2. Don't forget we've already done 3.1. before 2.5. So we're going to be considering the question of how to compute the length of a parametric curve. So there's a parametric curve. How long is it? How much pencil lead did it take me to draw that picture? And there's some setup of related objects and their connections that we need to set up here. And in particular, we're going to focus on looking at one little piece of curve, specifically a piece of curve that starts at one point and then ends, a short number of seconds later, right? So I was at the purple point. I have moved, or I will be moving to the dark blue point, and what can I write down in relation to that? And various things that we're going to relate are, for one thing, there's the linear approximation. There's the differential of this parametric curve. So called the position differential, because it's the differential, the linear estimate of the change in your position. And then there's there's the velocity, and there's the unit tangent vector, and the length of the piece of curve, and they're all related in some nice natural ways that actually don't take too much effort to go through. But we'll talk through those details next time, and this is going to be the foot in the door that will allow us to compute literally the length of a piece of curve. Y'all have a good one. See you later. Oh, and if you came in after I started the lecture, make sure that I get you marked down on attendance. And have a good Wednesday.